Hi there. This is problems 23 through 27 of the Unit 2 Trigonometry Review. And first, we're going to read the problem out loud. I recommend you do this with me. It says, put your finger right there, finger, not pencil, finger, because it forces you to read it twice. The angle of elevation from a point 64 meters from the base of a building to the top of a building is 35 degrees. Find the height of the building. Now we're going to highlight our key words here. We have an angle of elevation. We have a point that's 64 meters from the base of a building, distance-wise, and the angle of elevation is 35 degrees. So make sure angle of elevation goes over here, 35 degrees. And our ambition is to find the height of the building. So we're going to draw a storyline. It's always really important if you're dealing with anything on land that you draw a ground line, anything on water, you draw a water line. So we're going to start by drawing a ground line. And why that is important, because anything built against the ground, we're going to assume, unless we're told otherwise, that we have a right angle. So we have a building. So the building has the right angle. That's going to provide us what we can use SOHCAHTOA with. The angle elevation, 64 meters away, 64 meters away. So that means from the specifically from the base of the building. So this is going to be 64 meters. And the angle of elevation, this is really important to know the difference. Angle of elevation and angle of depression. Elevation, if you could do this with me, starts at a horizontal and goes upward. That's elevation. Angle of elevation, horizontal, up. Angle of depression starts also at a horizontal and goes down. Depression, horizontal, depress. So the main trick, if you will, an angle of elevation starts at a horizontal and goes upward. An angle of depression starts at a horizontal and goes downward. So your angle of elevation and your angle of depression are always going to be alternate interior angles. You're going to have parallel lines here. Angle of depression, angle of elevation. So just kind of keep that in mind. So just to distinguish one from the other, so here would be an imaginary line like this. And in this situation, your angle of elevation is going to be here, elevate, horizontal going upwards. And your angle of depression is going to be here, horizontal going downwards. But it will always be congruent because they are alternate interior angles. So in the storyline, let's see, angle of elevation, 64 meters. Find the height of the building. So this one, we're going like this. There's our X. And the height of the building. Oh, this is 35 right here, 35 degrees. There we took care of that. Notice I crossed stuff out. Height of the building, there's our question mark. Have, need, do is what I use. We have label. This is 35. That would make this the opposite side. This is the hypo. This is the adjacent. So we have the adjacent, which is 64 degrees. We need the opposite. So what do? We have an OA combo. So that's tangent, that's TOA. So that's going to be tangent of angle theta over 1 equals opposite over adjacent. I always write the equation. I do not immediately put in the numbers. You always write the essential equation beforehand. Now we circle, plug, chug. And tangent of theta, our theta is 35 degrees over 1 equals opposite, which is our x, over adjacent, which is 64. Don't touch a calculator until your variable is completely by itself. So I'm going to tan 35 times 64 equals x. You put that in your calculator. Tan 35 times 64, round to wherever your teacher wants you to round, and then go from there. Finger, not pencil, finger first, because it forces you to read it twice. You have to read it once with your finger and then once highlighting. So finger. The highest point in Texas is Guadalupe Peak. The angle of depression from the top of this peak to the smallest miner's cabin at an elevation of 2,000 feet is 26 degrees. The cabin is 1,400 feet horizontally from a point directly under top of the mountain. Find the altitude to the top of the mountain. Okay, again, it's a ground problem, so you establish a ground line. It's a land problem. Establish a land line. There is 0 elevation. You're going to need that. And the storyline involves Guadalupe Peak, which is the highest. This is Guadalupe Peak. Come up here, and as you account for stuff, we cross it out. Guadalupe Peak. The angle of depression from the top of this peak, so we're going to go from the top of the peak, and it's an angle of depression. So immediately, whatever we're doing, we know it's horizontal going downward. Horizontal going downward. Miner's cabin. Now, a miner's cabin is also 2,000 feet above the ground. So it's on a small, some sort of hill of sorts. So here's your cabin. So from the top to the miner's cabin, that angle of depression is 26 degrees. Additional pieces of information, you are already told that the cabin itself is 2,000 feet in elevation. And as you account for that, 2,000 feet, 26 degrees, the cabin is 1,400 feet horizontally from a point directly under the top of the mountain. So here's the top of the mountain. There's a point. Here's the cabin. So the cabin's like this. 14, and that keyword there is horizontally, and we're still in feet, so we don't have to worry about units. And our ultimate goal is to find the total height of Guadalupe Peak, which will go from here to all the way down. That's our question mark. What the trick to this problem is that you do have to realize the right triangle we're working with here, right here, okay, if you take that straight across, is 2,000 feet up. So at some point, we have to account for that 2,000 feet. So although that is your question mark, you're going to need to find this x. That x is going to be the same as, I'm going to draw it over here, this x. That's why I like to draw. The minute that I have angle of depression, I always just instantly draw a rectangle. And so that you can see both your angle of depression and elevation, creating alternate interior angles. So there's always a flip of two triangles going on. I call those alternate interior angles armpits of the Z. And that 1400 can come transfer from here to here, 1,000. Okay, so I'm going to use this triangle right here. Have, need, do. We have, in this case, this is the opposite side. And this is going to be our adjacent. And this is our hypo. So we have our opposite, or we want our opposite, excuse me, not have. We want our opposite, but we have our adjacent. So we start with that. We have our adjacent. And we need our opposite. So we got an OA combo. What do we do? Of course, that's tangent again, toe up. So it's tan theta over 1 equals opposite over adjacent. So we take the tangent of the circle plug chug. Our theta is going to be 26 degrees. Keep parentheses around that, equals our opposite, which is x, over our adjacent, which is 14,000. Cross multiply. And whatever x is, it's going to equal the tan of 26 times that 1,400. Now, that's not your final height. Whatever you get there, it's not your final height. I'm going to keep that in red. It's going to be in feet. Because when you solve for this triangle, you're still 2,000, feet off the ground. So whatever that is, you still have to add 2,000 feet to it to get your total height. Number 25. Said the Tower of the Americas in San Antonio is 622 feet tall. Find the angle of depression from the top of the tower to Jake's department store, 972 feet from the base of the tower, round to the nearest degree. Let's highlight our key words here. We have a tower. The tower is 622 feet tall. We're trying to find the angle of depression. Top of the tower to Jake's department store. Jake's department store is 972 feet away from the base of the tower. The land problem, so we're going to establish a ground line. Start with that tower. No idea what the tower looks like, but I'm assuming if it's tall, it has some sort of little antenna on it of sorts. Cell phone antenna, radio antenna, something like that. And it is 600 122 feet tall. And cross stuff out as I account for it. We want the angle of depression. Careful, angle of depression. Horizontal, going downward. Horizontal, downward. So let me show you the most common mistake. Here's Jake's department store. No, it's not Jake's. Joski's department store. Joski's, whatever. And so here's the most common mistake students make. Go like this. And students think that this angle right here is the angle of depression. But that's not the angle of depression because it's vertical going outward. The angle of depression is horizontal going downward. So our angle of depression, you have to draw in an imaginary horizontal line, and the angle that we're actually looking for is right there. I'm going to call it theta. Put it in red so there's no mistake. Right there, that's the one we're looking for, horizontal going downward. Other piece of information is 972 feet away. So we have a right triangle. So right here, our numbers are in this triangle, but the angle we want is in this triangle. So that's why you need to know about those alternate interior angles, because you can simply transfer that angle of depression to right here to the angle of elevation to actually find it. Because the angle of elevation and the angle of depression will be the same thing. But you have to be able to draw in that angle of depression. Because they're alternate interior angles. Why? Because horizontal lines are always parallel. So starting from this is going to be our opposite side. This is going to be our adjacent. And then, of course, here's your hypo. Have, need, do. We have the opposite side. And we also have the adjacent side. And we need, this time, a missing angle of depression, theta. So this time we use, what do? We're going to use inverse SOHCAHTOA. And we have an OA combo. That means it's tangent TOA. So that's inverse tangent, opposite over adjacent is going to give you that angle theta. So plugging our numbers in, we have tangent, inverse tan, parentheses, opposite, 622, over adjacent, 972. Check units, they're both feet, so we don't have to worry about converting units. And that's going to give you your angle theta. Wants you to round to the nearest degree. All right. This particular problem introduces the concept of bearings. So let's read it out loud first, and then we'll talk about bearings because that makes it just a little bit more interesting. The airline distance from Philadelphia to Syracuse is 260 miles on a bearing of 335. The distance from Philadelphia to Cincinnati is 510 on a bearing of 245. Find the bearing from Cincinnati to Santa Cruz. All right, so the number one thing you need to understand about bearings, and we're going to do this first, just a general concept. And the reason why this is consistent, because we're talking about navigating both on sea and on water. Therefore, you need to be 100% consistent. So pilots can talk to each other and they know where each other's are, and ocean vessels can talk to each other. And so there's 100% certainty. We know where there are, so there's no confusion. The concept about bearing is always measured from the north line, and it's always a north-south concept. So when we're dealing with north, south, east, west. So besides the fact that bearing is always measured from the north line, bearing is also always going to be clockwise. So when we talk about angles in bearings, it's from the north line and it's clockwise. So this is exactly, it's very different than when you're doing a unit circle, where when we measure angles, you start at this quadrant 1x line, and then we go around like this. It's counterclockwise. So that's just kind of an important caveat. That's the difference between the unit circle and dealing with bearings. So as you work with this bearings problem, you're going to be drawing a lot of north lines in order to identify this. So it says that we have an airline from Philadelphia to Syracuse is 260, bearing 335. The distance of Philadelphia to Cincinnati is 510 on a bearing of 245. Find the bearing of Cincinnati to Syracuse. So you notice that Philadelphia is mentioned twice. Philadelphia, Philadelphia. So Philadelphia is kind of the center point. I'm going to start at Philadelphia. So I'm going to draw, and there's bearings for all of these. So I'm going to draw a north line for all of them, and I'm going to use a straight edge to make this a little bit more consistent. So I have Philadelphia to Syracuse. Do Syracuse in blue. And that also involves a bearing. And then you also have a third point, Cincinnati, seems to be going a different direction. And bearing. Okay, so there's all our bearings. One little trick of the trade, just like when you're dealing with horizontal lines and angle of elevation and depression, it always involves parallel lines. When you're dealing with bearings, because bearing by its nature is always dealing with the north line, when you draw it, they look vertical. So you're also always dealing with parallel lines. So in both circumstances, you need to watch out for those alternate interior angles. I call them armpits of the Z. And under bearing problems, it's going to look like this, alternate interior angles like this. Again, I call it armpit of the Z, sideways, anyways. So watch out for those parallel lines. That's the piece of background information you need to have. So for the first one, from Philly to Syracuse, you have 260 miles. and you have a bearing of 335 degrees. So starting from this north line, we go 335 around 335 degrees, and that is the 335. And so step one, we want to get this little angle here because it's going to be helpful to us. Even if it isn't, you should just get it anyways. So that's, of course, going to be 360 minus 335. And we're going to get 25 degrees angles here, 25-degree angle. And then it says the distance from Philly to Cincinnati is 510. And its bearing is 245 from the same point. So when you go like this, 245, 245, again, that's going to be, you can see it just gets past 180. So what I want to find is this angle here. So I'm going to do 245 minus 180. Make it 65. So that's just all set up. What we're asking is this, the bearing from Cincinnati to Syracuse. So if I were to connect Syracuse to Cincinnati, but we're ultimately trying to find, and that's kind of important to make sure you peg what you're trying to find, is you're trying to find this angle right here, Cincinnati, from the north line, because it's a bearing, that turn, if you will. So that is the angle we're trying to find. That is our bearing angle from north, from Cincinnati back to Syracuse. So keep in mind, that's the little angle we're ultimately trying to find. And I call that angle theta. So now we're going to see what other kinds of information we have here. Here's kind of what I would call the trick to the entire problem. Look very carefully. This is 180, of course. So if you add 25 and 60, 65, excuse me, 10 carry the 1. Oh, looky there, 90 degrees, which implies, even though I didn't draw it accurately, that this is the magical 90-degree angle here. And we need to define something that can help us with theta. And notice we could easily find this angle right here. Because I already labeled that theta, I'm going to call that alpha. So we are going to find that alpha angle. So that's going to be tangent of, whoops, you don't know why it's tangent yet. I do, but let's talk about it. So from that angle, the 216 is going to be our opposite side. And the 510 is going to be our adjacent side. So we're using inverse tan. So inverse tan, parentheses, opposite over adjacent is going to give us that angle alpha. Inverse tan, our opposite is going to be 216. Our adjacent is 510. That's going to give us our angle alpha. So because this requires another step, I'm going to take it there. So it's inverse tan 216 and 510. Okay, my calculator just goes the other way. So 216 divided by 510. Hello. And then second function tangent, I get 22.95. I'll take it to the second decimal. I'm not sure which decimal your teacher requires. 22.95 degrees. Okay, let's get real close up here. So what you just found is this little angle right here, 22.95 degrees. You're trying to get that red angle. And you're like, I really wish I knew what this whole thing would be. Because if I knew that, I simply subtract from it. Well, you do know that because you have parallel lines. You have alternate interior angles rocking here. See that? I'm going to kind of drag it out real big so you can see. Okay, you have alternate interior angles, which means this 65 comes over here to this 65 because they're alternate interior angles. So to get that bearing angle, which is the red one, that's going to be 65 degrees minus the 22.95 degrees, depending, or if you want to round that, I'm not sure where your teacher wants to round it. And that is going to get your bearing angle theta, which is right there. So to recap, bearing is always taken from the north line and it always travels clockwise, which is different from the unit circle when you are starting at 0 degrees here on the x-axis and it always goes counterclockwise. So the unit circle and bearings are not interchangeable. All right, last problem here. It says a ship travels, a finger, again, lips moving out loud. Ship travels 70 kilometers on a bearing of 35 degrees and then turns on a bearing of 125 for 180 kilometers. Find the distance at the end of the trip from the starting point. Now we filter. We have it traveling 70 kilometers on a bearing of 35 degrees. And it turns on a bearing of 125 for 180 kilometers. Find the distance from the end to the start. Find the distance from the end to the start. So I'm going to hit start. This is our starting point. And draw my bearing line, which is north. And bearing of 35 degrees. So we're going to go like so. 35 degrees. It helps if you kind of draw it to scale. Doesn't have to be to perfect, but 35 shouldn't actually, that's closer to 70. Let's squeeze that up a little bit. 35 degrees is more like this. Okay, so we got 35 degrees. So we're going to travel along that distance for 70 kilometers. 70 km. And at this point, we take a turn. So at that turn point, again, we draw a north bearing. We'll make your little notation. These are parallel to each other. That's going to come into play. And it turns on a bearing of 125. So that's going around like this. 125. A little past 90, 125. And we're going to travel for 180 kilometers. So it's a little more than double here. So that's our turn. Here's our end point. And the ambition is to find this distance, which is X kilometers. So let's take a close look at what we have here. On this side, we have alternate interior angles. So boom, boom, boom. We can bring that 35 right over here. This is, of course, 180. So we just figured out that this angle here is 55 degrees. 55 and 35. Oh, look at there. There's our 90 degrees. So we do have a 90-degree angle right here, which means we can use standard SOHCAHTOA. I mentioned law of sines and law of cosines. You can use law of sines and law of cosines even when you don't have a right angle. So that's something we're going to go over sometime. But since you're only using standard SOHCAHTOA, you have to have some sort of magic right angle around there somewhere in order to use it. But law of sines and law of cosines can be used even when you don't have a right angle. That's why they're magical. So let's take a look at what we have here. Well, we have one length already, which is 70, and we have another length here, which is 180, and we need this third length here. And now we just have a standard Pythagorean theorem of one leg squared plus the other leg squared equals the hypo squared. You would know this as a squared plus b squared equals c squared. But I never use that version in my class. I use the descriptive version. So we have one leg is 70 squared plus the other leg Notice I'm circling as I plug stuff in. That keeps you from losing track. So bottom line is x is going to be the square root of 70 squared plus 180 squared. And I do it like that because once your x is by itself, you can put all of this in your TI-84 in one fell swoop, and you don't have to do multiple steps.